Okay, guys, so here's a new scenario and one of the more useful things that I found when utilizing STK. It's the use of an iterative modeling software known as STK Analyzer. Now, Analyzer is a paid license that you can have attached to your STK that unlocks some very user-friendly iterative modeling processes. And what's great about STK Analyzer is it plays very nice with other data spreadsheet tools like Excel, and it works very well with all of STK's native components like Astrogator. So what's the value of this software? Well, here I've created a completely academic scenario of the International Space Station currently going through its orbit above the Earth, and it's going to cross paths with some drifting debris. And as you can see based on these incident lines, there's going to be a potential close approach in approximately 5 minutes from what I'm currently depicting. Now, the point of this closest approach is just over 410 meters, which is lucky for the space station, but ultimately we would never want to let anything, to my knowledge, get that close to the International Space Station. So essentially what I'm going to do as my design scenario is, if I noticed that this debris was going to be a factor for the ISS 5 minutes prior to this point of closest approach, and the ISS conducted and successfully executed a burn, which direction of burn would give me the biggest miss distance with respect to that debris? Now for this scenario, it's going to be purely academic. I don't know exactly the multi-face aspect of the ISS thrusters, nor how long it would take to apply some level of delta V. However, I'm just creating this academic scenario to demonstrate the modeling power of STK Analyzer. So for this, I'm going to be simulating impulsive thrust, meaning instantaneous application of thrust. And I'm going to be allowing the ISS to apply that thrust in any direction. So now that I have my scenario, how am I going to start to analyze and break down this problem? Well, one thing I could do is simply guess the direction of burn that I think will make me the most successful. Again, the number that I'm trying to beat is 410 meters of close approach. So let's go ahead and see how we would build that out. So what I'm going to do is insert a new satellite object, and it's going to be define properties, and I'm going to set it up as an astrogated object. That's because I'm going to be doing some maneuvering, and I want to make sure that I have a fully maneuverable version or variant of the ISS. This current ISS is just based on a TLE and does not actually have the ability to become an astrogated object. So instead, I'm going to take advantage of one of the features of Astrogator that I haven't shown you guys yet, which is the follow command. So I'm going to delete my initial state because I'm not going to define my orbit. I'm going to let my orbit follow something else. In this instance, what it's going to follow is going to be the International Space Station. And I'm going to follow that up to the point that I would prefer my separation event to occur, e.g. when the maneuver occurs. So let's go ahead and define that by an epoch, and we'll delete the duration. And now what we have here is a satellite object that is going to follow the ISS until it gets to this time. In which case it's just going to propagate on. So let's just model that and see what it's going to look like. So you can see the two objects, and indeed the ISS and my new modeled astrogator are following the same track. And as you can see, the ISS maneuver satellite, which is the astrogated version of the ISS that I've created, has that same close approach with the debris around this time, 2010 and 31 seconds. Okay, so let's just go ahead and back up the clock by 5 minutes. And let's just let this object maneuver in a particular direction. So through some Google Warrior searching, I was able to find that the ISS uses about 2 meters per second a month for its altitude management. So what I'm going to do is I'm going to execute a spherical burn, and I'm going to do just 2 meters per second. Now at the current azimuth and elevation, that's all going to be applied radial, which, honestly, thinking about it, probably represents a relatively good strategy for the International Space Station, just based on the short duration between this maneuver and the collision event. So let's go ahead and model this and see how far we get. So now with that maneuver, we can see that the closest the ISS maneuvering got is now 630 kilometers. So a positive radial burn seems to be somewhat successful. What about a negative radial burn? How far is that going to get us? So easy enough, we'll just turn our azimuth to be 180 degrees. And now we have a purely negative radial burn. And that actually seems to have been much more successful. Now the ISS's closest approach to the debris is 900 meters. How can I be confident that this is the closest approach? The way I set up this satellite and its propagate is I use a user select where the user value that I'm calculating is the range rate with respect to an object. And I set it at 0 kilometers per second. And the object I set it with respect to is the debris itself. And how I set this propagate up is very important for us to validate this technique of using Analyzer to change a scenario. Before I move into Analyzer, I just want to do one more thing. Right now I've seen that a negative radial burn is much more successful than a positive radial burn. What about an in-track burn? Here we can see an in-track burn was actually apparently less successful than the negative radial burn. In fact, it was so unsuccessful that it got worse than our original target of 400 meters. We're now down to just 40 or 80 meters. Yikes. That's why you don't want to guess and check your way to a solution. Okay, but that's basically what we're doing. We're guess and checking different directions, and we're trying to see what is the net result of that. So that's all well and good, but ultimately not the most successful way to design a scenario. So instead, what I'm going to do is let STK Analyzer guess every single possibility for direction of a burn and see which one gets me the furthest from this piece of debris when applied. So what I'm going to do is try to decide what are my design elements for the iterative modeling, what are the constraints, restraints, and what is the end result that I'm looking for. So from here, at least, it's intuitive. What we were doing is the design elements, the variables in this scenario, are the azimuth and elevation, e.g. the direction of the burn that we're applying. Our constraint is it has to be 2 meters per second, or the monthly allotment for the ISS's orbit keeping. And the point that we're looking for is the range distance to our target object. And we want to measure that range at our point of closest approach, which I've set up this propagate to intuitively provide us. So all I have to do is go and find what that range is. So let's go ahead and open up results of this propagate. We'll go to relative motion, we'll go to range, we'll use a specified reference. In this instance, it's going to be the debris. And we'll click OK. All right, so now I just want to reiterate, because the setup and design of this experiment is very important for Analyzer to actually provide us anything of value. So essentially what we've done is we've created two variables, which is going to be the azimuth and elevation of our burn, which just define the direction of the burn in radial in-track or cross-track motion. And we have a magnitude of burn that we're going to set fixed at 2 meters per second. And then when we get to our point of closest approach, which we've created in which we've uniquely created through the use of a user selected value of range rate with respect to a target object. At that time, at our time of closest approach, we're going to check a result of our range to that object, which is the outcome of whatever modeling we're going to be doing. Great. So with all of that, let's go ahead and fire up STK Analyzer. To do that, we're just going to right-click on Maneuver, and we're going to go to Satellite Plugins and STK Analyzer. Okay, and within STK Analyzer, there are a lot of different objects that you can perform analysis with respect to. We know that ISS maneuver is the object of our greatest interest, and all of the values that we are trying to manipulate are within its propagator of astrogator. So let's open up that, and we can see here are those objects. We have a follow, a maneuver, a propagate, and a propagate. And if you remember the window of this object, you can see right here that it has a follow, a maneuver, a propagate, and a propagate. And within maneuver, our design variables are going to be these here, the azimuth elevation. And so what we're going to do is find those design variables inside of Analyzer. Let's open up maneuver. And that's part of the impulsive thrust vector, which you can see on the window. We have thrust vector, impulsive. So let's go ahead and open up that. And there, sure enough, there are the azimuth and elevation. Magnitude and everything else is in there, so these could become design features for a different type of experiment. But for now, we don't need to worry about those. And as you'll recall, we put the range inside of the first propagate, which is that one that gets to the point of closest approach with respect to the object, and then checks the range. So that's under the results of that propagate for range. Okay, so now we have two inputs and a single output. Of the options we have, and we have many up here, the one that is best suited to the experiment that we're currently attempting is going to be a carpet plot. The reason a carpet plot is useful is because it allows for two inputs and as many responses as we want. The number of responses is not super critical, but as you'll see, the number of design variables is a huge factor for how long this run is going to take. Okay, so our first value is azimuth, and azimuth can have values from 1 to 359 degrees. Really 360, but that's equivalent to 0. And elevation can have ranges from -90 to 90. Now, it's very important to set the number of steps or the step size that you want to iterate through. For instance, if we were to set this to 1 for each of these, that would mean that STK would check every single value between 0 and 360 and -90 to 90 against each other. So essentially, STK will model 0, -90, 1, -90, 2, -90, 3, -90, 4, -90, so on, until it has modeled every option and checked what the range was after it ran that option. Now, why that becomes so critical is that's 360 times 181 runs to execute, which is 65,160 runs. Personally, I don't have the desire to wait for that level of precision, and I'll show you why you don't actually need that level of precision, especially as you're doing your first run. Right now, because we are sort of taking a shot in the dark and saying, I'm not sure exactly what the best value will be, but it's definitely in this space somewhere. It's much more to our advantage to set our number of steps to a more reasonable amount. So let's just go 20 by 20. So now we have a manageable 400 runs that STK will very quickly be able to solve through. We'll find out what the best of those 400 was, and then we will refine our search into a more precise level of runs. So let's go ahead and click run, and we'll watch how this software works. So there you can see it's creating the 400 runs, and away it goes. It's just going to start calculating the range after it conducts a burn. So here you can see it did 0, -90, and it got a range of 840 meters. 0, -61 was 820 meters, and so on and so on. And if you go back to STK, you can actually watch these iterations happen in real time as it attempts to find the point of greatest range. Now this chart is very easy to export into Excel, but Analyzer comes native with some different graphs. So let's go ahead and add a contour plot. Okay, so you can watch this graph fill in real time, kind of interesting. and we can start to make certain inferences. What we can see here is this is our azimuth. Currently it's only checked up to 335 degrees, but eventually it'll get to the full 360. And this is our elevation. And it looks like the way the software is working is it's checking through each of the elevation points against each of the azimuth points. And right away we can see that there is apparently a relationship between a negative elevation, so a highly cross-track maneuver, and potentially a low azimuth, so a high radial maneuver. As you can see, the runs are going to take another 5 minutes, so I will just do the magic of video editing, let the software finish, and then we will try to draw some conclusions.
One eternity later.
Okay, I thought you guys might want to join me for the last 20 seconds of our completed runs. And there we have it, a complete analysis of the scenario that STK was presented. It looks like somewhere in this space is the most range we were able to get. As you can see, range is getting higher as you go up in color. And it appears that somewhere at azimuth of 245 and elevation of negative 33, we hit sort of a maximum range where we get a 1 kilometer missed distance. Let's just go ahead and head back to STK and model this and see what it looks like. Okay, so 245, negative 33. And indeed we can see at 245 and negative 33, we have, through 2 meters per second, greatly increased our closest approach to the debris, over 1 kilometer of missed distance. What if we were to employ one of the worst burns? So it looks like there's this interesting minimum right around 94. So it looks like we hit kind of a minimum, let's see, 340.61. Let's model that one and see what that looks like. So here we have 340.61, 2 meters per second. Let's see what we get. Sure enough, that almost steers directly into the debris. Not what you would want. It looks like the close approach is almost the size of the ISS itself. Indeed, we can see we have only 40 meters of missed distance with respect to our target. Okay, and now from this space here, this dark red, we could run the software again, and this time only let our values go from 200 to 300 and 0 to negative 90. And rather than incrementing at 10-degree intervals or 5-degree intervals, we could move at half-degree intervals, and we'll find a better and better value in here until through iterative modeling we have found the best possible value. Now, in terms of why this software matters, I'll just say that even with extensive experience working and thinking about objects moving in space, I don't think there's ever any way that I would have intuitively guessed that having negative cross-track and some negative radial and in-track maneuver, so equisplitting the direction of the maneuver between the three values, was my best option. Unfortunately, even with CW equations, it would have taken me a long time to come to that conclusion, whereas STK Analyzer, when you are using this software and get really good at setting up your design experiments, you can come to a conclusion almost in the span of minutes. Especially if you have fast processing speeds, you could solve to a high fidelity in less than 20 minutes. Again, this was a notional scenario. Obviously, we would have solved 5 minutes too late for the ISS to miss just based on the processing power of my laptop. However, if there's ever a scenario where I need to know what is the best direction of burn to avoid a piece of debris, STK Analyzer might be able to work within the timescales that you are executing in. Perhaps better than some of the other software that you may have available to you. And more than just maneuvers and the ability to avoid debris, STK Analyzer can take essentially any data point out of STK and turn it into some sort of trade study. There's just so much data being actively tracked in STK that any one of these values could eventually become a variable for one of your trade studies.